Section 4.5 optimization problems. Because we need the tools in section 4.1 to solve the problems in this section. So let's take a review about section 4.1 first. Section 4.1 is about maximum and minimum function values of a function over some interval. Review number 1. Whether or not a function has an absolute extreme value depends on the interval of interest. Here we have two figures about the same function f. The figure on the right, the figure on the left, I consider the portion of the graph of function f over this closed interval. Because the interval is closed, it contains the two endpoints. So at the two endpoints, I add solid point here. That means that I consider these 2 points as part of the portion that I am considering. Now this portion has a highest point, this point. So this point is the maximum function value of this function f over this closed interval. And also this portion has a lowest point here. So this point is the minimum function value over this interval AB. Now, the figure on the right. I consider the portion of the graph of the function f, now this time, over an open interval. Open interval doesn't contain the two endpoints. So I place open dot here. That means that I don't consider these 2 points as part of the portion that I am considering. Now, this portion of the graph has low highest point because this open dot is not part of the portion that I am considering. So this portion has low maximum value. But this portion has a lowest point, still has a lowest point here. So the function has a minimum value here over this open interval, but it doesn't have a maximum value over this open interval. So that's why I say that whether or not a function has an extreme value, maximum or minimum, depends on the interval of interest. Review number 2, extreme value theorem. This theorem says that under some conditions, it is guaranteed a function has a maximum value and a minimum value over an interval. Yeah. Extreme value theorem says that a continuous function, first, the graph of the function should be continuous. On a closed interval, the interval should be a closed interval, not an open interval. Then the function must have an absolute maximum value and an absolute minimum value on that interval. Yeah, exactly this case. The graph is continuous and the interval is a closed interval. Then guarantee that the function has a maximum and a minimum over this interval. Extreme value theorem only says that we guarantee the function has a maximum and a minimum, but this theorem doesn't tell us where the maximum and the minimum are. So to locate the maximum and minimum, the location of the maximum and minimum is based on this observation. This observation says that a function is continuous on a closed interval. So by extreme value theorem, the function has a maximum and a minimum. Then maximum and minimum can only appear at the following points. Only at the following points. Maximum and minimum cannot appear at other points. Maximum and minimum can appear at n points. This is one example. And they can appear at interior critical points. What is a critical point? Take a review. A critical point is a point in the domain of the function f of x. I miss f here. Where at the point C, derivative is 0 or doesn't exist. Derivative is 0, tangent line is horizontal. Derivative doesn't exist, the graph has a corner there. So a critical point is a point in the domain where tangent line is horizontal or the graph has a corner. Maximum and minimum can appear at an interior critical point. Interior means inside the interval AB. Okay, now based on this observation, we in section 4.1 develop 3 steps to locate maximum and minimum function values. These 3 steps, the book calls them the closed interval method. You can find this method on this page. To find the maximum and minimum values, here maximum and minimum means absolute maximum, absolute minimum. To find the maximum and minimum values of a continuous function on a closed interval, step 1, find all the critical points inside the interval between A and B. Because maximum and minimum can appear at critical points, so we find all the critical points. Step 2, compute function values at the critical points and also at the 2 endpoints. Maximum and minimum can also appear at endpoints. So we also compute function values at the 2 endpoints. Now, step 3, make conclusion. The largest function value in step 2 is the maximum function value on this interval AB. And the minimum and the smallest function value in step 2 is the minimum function value on this interval AB. This is the closed interval method. Continuous function over a closed interval. Okay, now when the interval is an open interval, say this case, okay. When the interval is an open interval, low guarantee, the function has a maximum function value or a minimum function value. Then how to locate a curve over an open interval, open interval. Here is the open interval method. This method says that this open interval method is from me, not from the book. So you cannot find this method in the book. You cannot find this method in section 4.1. To find the maximum and minimum values of a continuous function on an open interval. Now this time, no guarantee, the function has a maximum or a minimum. Also 3 steps, find all the critical points inside the interval, because if the function has a maximum or a minimum, then the maximum and minimum can only appear at a critical point. So step 1, find all the critical points between A and B. Step 2, now this time, is different from the step 2 of the closed interval method. Step 2, I suggest roughly sketch the graph of the function f. Roughly. Here, we just need increasing, decreasing. We don't need concave up, concave down. Roughly sketch. Now, based on the sketch, make conclusion. Okay, now in the following, I will show you examples about these 2 methods to solve optimization problems. I suggest the following steps to solve the problems in section 4.5. Step 1, draw a diagram. Step 2, assign variables. Step 3, determine what are given to us and what we need to find. Step 4, apply either the closed interval method or the open interval method to solve the problem. Okay, now example 1. A farmer has 2,400 feet of fencing, and he wants to fence off a rectangular field that borders a straight river. Yeah, this is a diagram. He leads low fence along the river, okay? Along the river, low fence. Now the question is, what are the dimensions? How to choose the width, how to choose the length of the field so that the field has the largest area. Step 1, I am done. Draw a diagram. Now step 2, assign variables. I let x denote the width of the field, y be the length, and a be the area of the field. Please note that this section 4.5 is different from section 3.11. 3.11 is about related rates. In 3.11, we also need to assign variables. The variables there all depend on the time t. They are functions of the time t. But here, in this section, the variables, they don't depend on the time t. They are not functions of the time t. Step number 3, determine what are given to us and what we need to find. The fencing material is 2,400 feet. This is given to us. Mathematically, it is x, the width, plus y, the length, plus x is 2,500. Yeah, we are given this equation. Now we need to maximize the area. Rectangular field area is equal to x times y. So the question is how to determine x and y so that A is the largest. From the given, I solve this equation for y, then I get this. Now I plug in this equation in the area equation, then I get area is equal to this. So area only depends on x. The range for x is between 0 and 1200. X cannot be negative because x is the width of the field. The width cannot be a negative number. X cannot be greater than 1200. When x is greater than 1200, to satisfy this equation, y must be negative. But y is the length of the field. Length cannot be negative. So x is between 0 and 1200. Now the question is, here, the question. Between 0 and 1200, you need to determine a value for x so that A is the largest. Here, for better understand the problem, here I plot the graph of this function. A depends on x of this function here. The graph is a parabola because the leading coefficient, the coefficient of the highest degree term is negative. So parabola, so the graph is a parabola open downward. Yeah. So this is the whole graph of A, whole graph of A. But we don't consider the whole graph of A. We only consider between 0 and 1200. Yeah. We only consider this portion. Now the question is, we need to determine the highest point. The highest point is here. Then what is the corresponding x? We need to determine x. Okay. Here are some cases. When x, you can choose x, say, to be 2200 to keep this equation. Then y is 100. Yeah, in this case, the area of the field is 2200 times 100 is this number. You can choose 1000 for x. To keep this equation, then y has to be 700. 700 times 1000 is this area. Or you can choose 400 for x, then y must be 1000. So area is this. So for different choice of x, areas are different. Now the question is how to choose an x so that area is the largest. That is the question. Because we need to determine the highest point of the graph of the function A over this closed interval. So we apply the closed interval to solve the problem. Closed interval. Yeah. Closed interval has 3 steps. Step 1, find critical points inside the interval. Yeah, between open interval, inside, between 0 and 1200. To find critical points, take derivative on the function. take derivative. Then set derivative to 0 and solve this equation. So we get one critical point. Yeah, between 0 and 1200. This is the critical point. Now, step 2 of the closed interval method is compute function value at the critical point. Yeah, function value. Plug in 600 in x here to get function value. And also compute function value at the two endpoints of the interval. Yeah. Left endpoint is 0. Plug in 0 in x here, then we get area is 0. Makes sense. When x is 0, the field has low width, so its area is 0. And the right endpoint, plug in the right endpoint in x here to get function value at 1200. 1200. Then the area is 0. Now, make conclusion. The largest function value is this. Yeah. So this is the maximum function value over this interval. So the answer to the question, the answer to this question is how to make the area the largest. You should choose x to be 600. The width of the field should be 600. Then the length of the field, yeah, plug in 600 here to get the length, to get y. The length of the field is 1200. So when the field is 600 by 1200, its area is the largest. This example, we apply the closed interval method to answer the question because the interval is closed interval. Now, in the following two examples, we need to apply open interval method to answer questions. The second example. Of all rectangles of area 100, which one has the minimum perimeter? Here I draw the rectangle. I let x be the width of the rectangle and y be the length of the rectangle. The area of the rectangle is 100. It is a constant. By the area formula of a rectangle, then we have this equation. X times y is equal to 100. Then what we need to find is we need to determine x and y so that the perimeter is minimized. From the given, we have y is equal to 100 over x. I plug in this equation in the perimeter equation to eliminate y. Then I get p depends on only x. P is a function of x. X can be any number between 0 and infinity. This is the range that x can change. For example, x can be a very small number, say 0.1. To keep area 100, y has to be 1000. For this case, for this rectangle, the perimeter is this number. X can be 1. 1 is not small, not large. To keep the area 100, y has to be 100. For this rectangle, its perimeter is 202. X can be a very large number, say for example 10 to the 4th. To keep area 100, Y has to be 10 to -2. And the corresponding perimeter is this number. So X can be any number, any positive number. Now the question is, between 0 and infinity, which number, which value for X, P is the smallest? Because the interval is an open interval. Then we apply the open interval method to answer the question. Open interval method has 3 steps. Step 1, find critical points inside the interval. Compute derivative on P with respect to X. Then we get the result here. Derivative on 200 over X, you can use quotient formula to compute its derivative. Okay, this I obtained this by quotient formula. Okay, derivative doesn't exist when X is 0. When X is 0, derivative doesn't exist. But 0 is outside the interval of interest. So we ignore 0. Now, second, to find critical points where derivative is 0, set derivative to 0 and solve this equation. Then we get X is positive 10 and negative 10. Again, negative 10 is outside the interval of interest. So we reject negative 10. So inside this interval, only one critical point. It is 10. Second step of the open interval method. Roughly sketch the graph of the function. Okay. Between 0 and the critical point 10, arbitrarily pick a point, and then evaluate derivative at the point. Then you will see that derivative is negative. Therefore, between 0 and 10, derivative is negative. The graph of P is decreasing by decreasing test, right? Derivative negative, graph is decreasing. Between the critical point 10 and infinity, arbitrarily pick a point, and then evaluate derivative at the point. Then you will see that derivative positive. So the graph of P over this interval is increasing. So therefore, we see that at 10, P has a global minimum. The global minimum value of P is P. Where is P? P is here. Plug in 10 in X, then we get the function value of P at 10 is 40. So 40 is a global minimum value. Now make conclusion. When X is 10, when X is 10, then the corresponding Y is X is 10. 10 times Y is 100. So Y is 10. So when X is 10, Y is 10. The rectangle, actually, that is a is a square. The rectangle, the perimeter is smallest. How small? Perimeter is 40. Example 3. A cylindrical can is to be made to hold 1,000 cubic cm of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. In order to minimize the cost of the metal, we minimize the total surface area of the cylinder. The question is essentially, it is find the dimensions that will minimize the total surface area of the can. Here I draw a diagram about the can. I let arrow below the base radius. The base is a circle. Its radius is arrow. And h, the height of the can. The volume of the can is a constant, 1,000. About the can, the volume is base area times height. So volume V is base area. Base is a circle. Its area is pi r square. Pi r square times height. It is 1,000. The can, the volume is kept 1,000. What we need to find is minimize the total surface area. I let A below the total surface area. It is base area times top area plus side area. Base area, base is a circle. Area is pi r square. Top is a circle. Area also pi r square. The side area, how to get the side area? Imagine that we use a scissor to cut the side and stretch out the side. Then we will see a rectangle. Area of a rectangle is base times height. The base of the rectangle is the circumference of the base circle. It is a 2 pi r circumference of the circle times height. So this is a side area. Simplify this expression by combining the first two terms, then we get the result. This is the total surface area of this can. Total surface area depends on R and H, but we can use the given to eliminate one variable. Say, for example, from the given, I can solve for H to get this equation. Plugging this in H, then H is gone. So total area is this. Then eliminate H, then we get this. Then cancel pi, cancel 1 r, then we get this. The radius r can be any number between 0 and infinity. For example, you can set r to be 1. To keep the volume 1,000, then H has to be this number. And the total surface area of this can is this number. You can set R to be a large number, say 100. The corresponding edge is this number, very small, 10 to negative 2 here. Then corresponding A is this number. You can set arrow very small, say 0.1, very, very small. And the corresponding edge is very large. So this can is a tall and narrow can. The corresponding total surface area is this number. So arrow can be any positive number. Now the question is how to choose arrow so that A is as small as possible. Because the interval is an open interval, so we apply the open interval method to answer the question. Step 1 of the open interval method, find critical points in the interval. Compute derivative on A with respect to arrow. Then we get this. Derivative of 2000 over arrow, you can use quotient rule to compute its derivative. From the derivative, we can see that derivative doesn't exist when arrow is 0. So 0 is a critical point. But this critical point is outside this interval. We are only interested in this interval. So 0 is outside this interval. We ignore the critical point. To find critical points where derivative is 0, we set derivative to 0 and solve for arrow. Then we get this critical point. This is a step 1. Now step 2. Roughly sketch the graph of the function A. Just roughly. We just need decreasing, increasing. We don't need concave up, concave down. Between 0 and the critical point, 5.42 critical point. Arbitrarily pick a point. Evaluate derivative at the point. We see that derivative less than 0. So the graph of A is decreasing on this interval. Between the critical point and infinity, arbitrarily pick a point, evaluate derivative at the point. We see that derivative greater than 0. So the graph of F is increasing on this interval. So therefore, see, at the critical point, A has a global minimum value. Now, step 3, conclusion. When arrow is 5.42, the corresponding H is 10.84. This can, its total surface area is the smallest. And the total surface area of the can is this number.